Okay. Let's just let me remind you, last session we've been talking about AC voltage controller. What we have is here the AC. Let's assume it is 230, the voltage and frequency 50 Hz in Oman. And here is my load R, and we have two anti-parallel thyristors, T1 and T2. Let's assume T2 is not there. If I plot the circuit, it looks like this. What we call this circuit? Anybody remember? What do you think? What we call the circuit? Khalifa, Abdul Malik, Shaima, Umayma.
دكتور
Yes.
ظهر هذا الشاشة ما ظهر الشاشة.
You sure?
Yes.
Everybody, you can't see in the slides? Hello? You can't see the slide or not?
No.
Only Khalifa or everybody? Ladies.
ظاهر دكتور
ظاهر خليفة. ظاهر بس عندك مشكلة.
ظاهرة دكتور واضح.
Great. So let me back. If thyristor here, T2 is not there. We have AC here, and we have one thyristor and one resistance and inductance. What we call this circuit? Do you remember? We studied this circuit before. Are you there? I need answer for this question. Here AC, here thyristor. The output will be like this, let me say. What we call this circuit? What is the output here? Is it AC or DC? What we call this circuit? Okay, you remember, but I will remind you. It's rectifier circuit. Is it? Did we study this circuit before? Hello? Are you there?
Yes.
Yes, great. So we call it half wave, you remember? We call it half wave rectifier circuit because we are only rectifying half of the wave, one switch. We have one switch here, right? We studied this before. Just we added here another switch. That's all. And this will make my circuit work in this way. Okay? So it will be positive, negative, not only positive. That's it. Now, this circuit actually, when we have positive part, this one, okay, the current will follow through the switch here to the load, back to the supply. Let me change the color. Okay. When we have negative, current will follow here in the switch back to the supply. You see the load? One time it see the negative or the positive waveform. That's all. Now, this is as a voltage controller. The only difference between this circuit and the circuit we discussed recently in the previous session is we added here inductance on the load. And while I'm talking about this, it's worth to mention that why R and RL load, why we focus more on resistive load or resistive inductance. We have other loads. We have LC, we have RLC, we have RC, we have different loads. We have RLC with back EMF and so on. But why we focus more on resistive and resistive inductive load? Now, because most of the application available in our world are resistive or inductive load, resistive inductive, especially in industry. When we go in, as example, I mean, the load in Oman is RL load. Why RL load? Because mainly the load in Oman is air condition and lighting. Mainly we use air condition and lighting. If we go to the appliances at home, we see that refrigerator is AC, RL load. air conditioners are all load, washing machines are all load, and so on. Most of the application at home, the inductive heating are all load, oven are all load. If we go to industry, in industry, what we have? We have machine, we have ovens. Both of them are RR load. So we focus more on RR load because most of our loads are resistive or resistive inductive load. Okay. Now, also, we discussed the effect of the inductance before, rectifier circuits. By the way, there is much similarity between this circuit and rectifier circuit. Now, what is the effect of inductance? Inductance will store energy at the beginning and it's released. So it makes delay because it's choke hanging the current. The current will not jump directly to the full load current. No, it takes time, increase gradually until it reaches the maximum. For that, we see that, yes, at this point, we trigger the thyristor and the voltage will appear across the load in this way, but the current will increase gradually. Okay, we reach here at pi, you see, the voltage reverse its direction. The thyristor should be stop conducting, but what happened, the inductance will enforce thyristor to keep conducting, even the voltage is negative, until it releases its energy at beta. Okay, alpha is the varying or triangular angle or delay angle, and beta is the extinction angle. The difference between them, it means beta minus, alpha equal delta. Delta is the conduction angle, how long the switch will conduct. Okay, we discussed this before. Just a minute. The circuit here is the supply voltage equal to the drop across the resistance and drop across the inductance. Ohm say this. Kirchhoff say this. Okay. So the drop across the inductance is LdI over dt. We studied this before. Ohms say Ri is the drop across the inductance, equal to the supply voltage. Now this equation, have we seen this equation before? Yes, we saw it, we deal with it in rectifier circuit. Did we solve it at that time? Yes, we solved it. Okay, let me copy paste it. What we already solved there at the beginning of this semester and put it here. We say that the differentiation of this equation contain two elements, I force and I natural. Force, it means the continuous, the steady state, which means V over Z. V is V maximum sine omega t over Z. Z is square root R square plus omega L square, and theta is the tan inverse, the imaginary of the real. It is there, it's supposed to be here, but I take it over, it will be in minus, so it will be minus theta. This is the forced. We discussed this before. Plus the homogeneous solution of the differential equation. First order differential equation, L di over dt, okay, plus Ri equals 0. Homogeneous, we solve it. We've solved it early in this semester, and you already solved it in level 1. Now, it will give solution constant, exponential, minus t over tau, where tau is L over R. When put it down and reverse it, it will be R over L. Okay. Now we need initial condition to find A. So we say, okay, let me back here. We have at alpha, the current is 0. So I will use this. Alpha current is 0. So when we substitute in this equation, we got the constant A. We take it back and substitute here. So the full equation is this. Oh, did we see this before? Yeah, we saw this before. We drive this before, the rectifier circuit. Now also you see here from the graph, at beta current will be 0. So when I substitute current here 0 and omega t by beta and simplify, I got equation. This equation contain beta here and contain beta here. I can use iteration to solve it to find beta. Okay, I can. We did this before. Okay. Now the main target for me is to find the output voltage. Output voltage will be from alpha to beta, the conduction from alpha to beta, V square and square root here. We convert sine into 1 minus cosine, definitely 1 over 2 outside, okay, by trigonometric. We integrate 1, it will be omega t. We integrate cosine, it will be sine, and we will substitute from alpha and beta. We got this formula, okay. Vs, always I have Vs, and I need only to have alpha and beta to find the output voltage. What about RMS thyristor current? Thyristor will conduct also from alpha into beta. Okay. Do I have the current? Yes, I have it. Just a minute, just a minute. This is the current. Where is it? This is the current equation. So I substitute here. This is square and this is square root. We cannot solve it directly. We need to solve it using numerical methods, either by software, by MATLAB, or any other software. So the RMS output voltage current is, we have two thyristors, right? So IR for the first thyristor and for the second thyristor square and square root, which gives me square root 2 IR. I need to first find IR, and then I can find I output. What about the average of thyristor? The same formula here. This is the RMS, the same formula, but without square root, the same formula. I think here we can easily integrate it because integration of sine is minus cosine. Integration of here, this is constant, so exponential only here. Now let me see the waveforms here. Vs is the sinusoidal input voltage. At alpha, the thyristor will conduct. This is the current. It will stop after pi at beta. Okay. When it conducts, the voltage, you see here, the voltage will appear across the load. See? This is. When it is not conducting, example here, the voltage is 0. No voltage across the load. This is open circuit. And what happens when it's the open circuit? The switch is open circuit. The thyristor is open circuit. What does it mean? It means it's blocking the input voltage. You see here, when it is open circuit, short circuit, open circuit here, okay? This voltage here, the part here is blocked. You see here, is blocked. You see here 0. The part here is blocked. Otherwise, if the thyristor conduct, it means it's short circuit. The drop across is 0, ideally. Now let's apply the previous equations in this example. Have a look. Single phase. Well, before I continue with the example, Khalifa, you see the slides? Khalifa, are you there?
Yes.
Okay, great.
Yes.
Great, thank you. Single phase, full wave controller. Single phase, it means one phase. AC, in this way. Full wave, it means I will control the two part of the waveform. So if I want to sketch it, I will sketch it in this way. Supply, just a minute. Okay. Supply are allowed. So there is resistance, there is inductance. Let's assume that this is the final year exam question. I'm working it this way. I'm reading here. I'm trying to put the circuit. Okay. Now just a minute. I know the circuit because I have it in the material. Where is it? This is the circuit, the same circuit. Oh, great. I have the waveforms, open book exam. I have all equations here, everything here, the waveform. That's great. Let me see how can I solve. Supply are allowed. The input RMS voltage is 120, 60 Hertz. Inductance given to me, resistance given to me, alpha given to me. Great, everything given. By the way, it's worth to mention that it's preferable to have alpha 1 equal to have alpha 2. Okay? Usually, this is how people they work for many reasons. Part of them reducing harmonics. Sometimes they can join them, as we will see later on. Join the firing circuit to have one firing circuit, okay, and many other let me say benefits. Besides, usually people and we as an engineer prefer to work in a balanced, stable, uniform system. The opposite, unbalanced, non-uniform, disturbed system is difficult to deal with. Okay. It's preferable to have everything organized. Okay. He asked me to find the conduction angle delta. Just a minute. I remember delta is beta minus alpha. Alpha is given to me pi over 2. I need to find beta. Did he give me equation for beta? Yes, he gave me. Can I solve it by iteration? Yes, I can. I will show you in the next slide. Now, okay, the RMS output voltage. Do I have formula? Yes, I have formula for this. The RMS thyristor current, I have formula. The RMS output current, I have formula. Average current of thyristor, great, everything given to me. You see here? Now, just a minute, let me. Okay. Now here I listed the information given to me RL frequency, so I can find 2 pi f, which is omega. Vs is given, alpha is given to me. Theta, I need to find theta tan inverse omega L. Okay, everything ready. Just a minute. Let me find beta because I need to find delta. I need to find beta. Just let me back. Do I have formula for beta? Yes, this is a formula. I use this formula by iteration. I find beta. Beta usually after 180. Let's assume it is 200 or 210. Trail and error will take you to beta. I use the formula, I got beta. By the way, when you substitute in the equation here, just a minute. We discussed this before, but I'm just repeating. When we substitute in, where is the formula? Just a minute. Okay. Now, when we substitute for the assumed beta, as example 200, if left hand side equal right hand side, this means that my assumption is correct. Beta is correct. If they are different and the difference is high, as example here 10, here 0.3. Difference is high, but here 0.1, here 0.15 as example. They are close, almost the same. So I can accept it. There is sort of error we can accept, but the difference here is large. Anyway, I got beta. I got beta here, 200. So just need to subtract, as you can see here. I got the conduction angle. Now the first part done. Okay, let me come to B. B, he asked me to find the RMS output voltage. Let me back. Do I have equation? Yes, I have equation. This is the equation. Just a minute. I have alpha, beta, just calculated. Vs is given equation. Just substitute. I substituted. I got the output voltage. Next, he asked me to find IR. Okay. I have here IR. By the way, usually I cannot bring similar to this part in final year exam as example, or in midterm exam. Why? Because this needs numerical simulation. You cannot do this in exam. We have limited time. So, but I'm talking about if you design, regardless the exams, if you design, you need to write codes here to solve this because it's not easy to solve. Anyway, by MATLAB, we solve it. We got IR. Now he asked me to find output current. Output current, as you remember in the previous slide, square root 2 IR. IR, I already got it. I substituted, I got the current. And to find the current in the thyristor, also I have formula. Okay, thyristor average current. I can use numerical also to solve it. I got the current. Now output power is I square R or V square over R, and I have both. It will give me the output power. Input power, volt ampere of the input. Vs is given the question. Usually we assume Is equal to Io. Okay. Then the output, the input current power is this. Now divide them, you go the power factor. Now this is for single phase AC voltage controller. What about a three phase? Three phase, just first of all, let me remind you with three phase. We studied this in level 2. We have three phases, VAN, VBN, VCN, across three points, three terminals, A, B, and C. Neutral is here. Now, voltage between A and neutral is VAN, which is maximum voltage. This is RMS, maximum voltage sine omega t. What about VBN? The same, but minus 120. What about VCN? Minus 240. Okay, because 120 is the phase shift between them. We deal usually with balance system. Now, if I want to find the voltage between A and B, I call it VAB. This will be V line to line, between two lines. What we do, we subtract VAN minus VBN. We use mathematics or trigonometrics to find the general form, and this is the general form. We have for ABC, AB, BC, CA, all of them. For each phase, we will connect anti-parallel thyristor, phase A, phase B, phase C. One for the positive, as you can see here, one for the negative. We give them sequence. You see here, this the positive here 1, 3, 5, while here 4, 6, 2. Oh, it's reminding you with the same sequence in rectifier circuit. The positive was 1, 3, 5. The negative was 4, 6, 2. Okay. And the load, as you can see here, are resistance. Usually we assume them identical because we are looking to balance system. Okay. Now, how this circuit work? It's work based on alpha. Okay, I will give example. I mean there is some range for alpha. It means alpha from 0 to 60. This give one formula. From 60 to 120 give another formula. You may say, why we have different formula? Because how many thyristors and which thyristors will conduct? This is the question. I give example here about alpha when it is between 0 and 60 and when it is between 60 and 120. Now first have a look at this graph here. This is the line-to-line voltages. Okay, it was plot based on phase voltages. Okay, and here are the triggering for each thyristor. Thyristor 1, 3, 5, 2, 4, 6. Okay, and we here make a dot line here to separate every 30. Okay, now if I come to alpha here, alpha here from here to here 30, from here to here 30, then this is 60. Okay, at this point we trigger the voltage for gate 1, thyristor 1 will conduct. Just let me back. Thyristor 1 connect to which voltage? VAN. So VAN will appear across the terminal here. Okay, that's great. So you see here from here this point, okay, to this point here to buy 120. This is 120, right? 120, 30, 30, 30, 30. 120. So because we know that each thyristor will conduct 120, and the thyristor 3, 5, and so on. At this point here, VA will conduct, and here G6, which is connected to phase B, will conduct. So the average will be VA plus VB over 2, which means VAB, okay, minus VAB over 2, it means 0.5 VAB. So this part is 0.5 VAB. Okay, from here, okay, let me change the color. From here to here, the second 60 with 30 plus 30, okay, it will conduct with this thyristor of gate 2. It's connected to which voltage source? To VC. So it will be 0.5 VAC. You see here, this part will be 0.5 VAC. Okay. Now here we have 0. Okay, we have 0, and we don't have positive connection now for this one. So this is VAN. I'm talking about VAN, by the way. VAN is not conducted to the positive, so we have 0. And it's returned back when the thyristor 4, which is on the same leg, because you remember. Let me show you. Thyristor 1 and thyristor 4 connected to the same leg. So here you can see 0 volt, and so on. We look to which thyristor will conduct. It tell me which voltage will be on the output. Then we find the voltage. Now, okay, what about 120? 120, it means from here to here. We apply the same thing, but we find that the voltage is different now. This is how it look like the voltage. Small pulse, 0, well, discontinuity, highly discontinuity. And the same thing for this one. Okay, if I take this and try to put it in a forms, we have equation, output voltage equation between 0 and 60, between 60 and 90, between 90 and 120, and so on for each one. Okay, now I don't need to talk about each one of them. I will only focus on this one, which is from 0 to 60, because I just discussed it here. Okay, I discussed it here. This is the general form for RMS. I will integrate VAN. Okay, so let me back. I will integrate from here to here 0, integration of 0. From here to here, integration of 0.5 VAB. From here to here, 0.5 ASC. From here to here, 0. From here to here, 0.5 VAB and so on. You got it? These are the parts. When we do the integration, we got the formula. What you need to use is the formula. You don't need to drive this one. It's there. Okay. Our interest here in the final formula to be used, as I will explain in the next example. Okay. What we have here, we have alpha. We have is easy. Just need to do the calculation. The same thing could be applied for the second, let me say, range, and the third, and so on. Also, it's worth mentioning, sometimes the load came with its controller, AC voltage controller. I mean, this is the load, okay? Inside, internally, it comes as a closed box, black box, okay? Inside, as example, motor come with its and the winding, okay? We will explain this in the application when we reach the drive, AC drive and DC drive. We have at each phase, there is AC voltage control to control positive and negative parts. Example, a 3-phase full wave controller shown in figure. Supply Y connected resistive load. Resistance is given to you here. Voltage is given to you. Frequency given to you. Alpha given to you. Everything given to you. Find the RMS output phase voltage. Just a minute. Let me see the alpha. Pi over 3 means 60. Oh, I have formula for 60. This is the formula. I will use it. Great. What he also asked me to do, the input power. We know output over input, okay. The expression for the instantaneous output voltage of phase A. I have the waveform. Okay, I will back to it. Okay. Now I have everything here. Let me start. What I will do, I will come here, substitute for VS by its value 208, alpha by 60 here, 60 here, and then here we are. We got the output voltage. Easy, yes. But what I want you to do, by the way, in all examples discussed until now, not only in this session or in this topic, which is AC voltage control, every topic we discuss, you will understand definitely the example. But I advise to use calculator, pen and paper, and try to do it by yourself. See the numbers, interact with the calculator, and so on. Now, what about the current? Current, we will divide voltage over resistance, as ohms say. What about the output power? 3 times I square R. What about the input power? Input power is 3 VS IL. VS 208, IL is the current, 10.09. We got the power. Now, if I divide them, I got the power factor. You see here? I got the second part. Last part, he asked me to find the expression for the instantaneous output power, the output voltage of phase A. Now, just a minute. This is the voltage of phase A, as you can see. So, from 0 to 60, the voltage is 0. From 60 to 180, 120, the voltage is this one, which is 0.5 VAB. From 120 to 180, the voltage is this one, which is 0.5, and so on. So I just follow the formula, the waveform, sorry. And just, by the way, VAN, we need VAN. We have the voltage VS 208 here, sorry. And we find it. Please check the number, maybe here in the editing. Okay. Now, VAB, VBC, VCA, I have the formula. We just mentioned it. Now let me start. Okay. I will say from 0 to 60, the voltage, as I mentioned, 0. From 60 to 180, is VAB over 2. It means 0.5 VAB. Do I have VAB? Yeah, I have it here. I just multiply it by 0.5. From 120 to 180, it's 0.5 VAC. Do I have VAC? Yes, I have it here. I just multiply by 0.5, and so on. So on for the other parts of the circuit. 1 second.